So this is the fourth part of this lecture on the Ax-Schanuel theorem for the G function. For the J function, and the fourth part will be called, let's say, the main theorem. So the main theorem is a little bit, I would say, it's not completely more general, but it's it can be applied to more general situation than the original Ax-Schanuel for the J function, but it will not give us the full theorem. As I said, it will just give the polynomial relation between the values taken by J in two of the formal power series we are looking at, or the convergent power series we are looking at. So this theorem, I can write the statement here, and then we will see the way we can prove that. So it's a theorem, maybe I have to give names. So it is Velázquez Sanz, myself, James Freytag, and Ronnie Nagel. Yeah, so this theorem is the following. So your X is your algebraic variety, smooth algebraic variety. G is your group. You have the projection on X. Let's call it PR for the projection. Okay, X algebraic. Smooth over C and G algebraic group. Algebraic linear group, algebraic subgroup of GL n of C. Okay. On this place, you take differential equation, and you have your principal form here that I will write U du, u minus 1 du minus u minus 1 a u, with A, which is a matrix of one form. The shape of the matrix is given by the group, and inside you have one form over X, and there are regular one form. At this level, there are some poles here. You just take the pole out of X. Okay. Then you have selected a leaf. Omega equal to 0 in the graph of a solution. A solution is seen as a function from X to G. And it exists because of the integrability condition. Remember that we impose to this form to satisfy d omega is minus omega wedge omega, or you can write on the matrix A, dA equal A wedge A, without the minus. And then on L, you have a small curve gamma. Gamma is a germ of curve, analytic curve, or in the leaf. So I will write gamma for the parametrization of the curve, and I will write gamma also. Gamma will stand for the image. The image also. Yeah. Okay, then this is our pattern. You have your variety X, you have your group here, and you have a leaf in the product, and you pick up some small curve in the leaf. Or it can be bigger curve, but you're just interested in the small parametrization of this one. And then you want to understand something about the risky closure of this leaf. So you have some hypotheses. So assume, so the first hypothesis is that your leaf is a risky lens. I will use the notation we already used. And yeah, your leaf is everything. X cross G, that you can rephrase that saying that the Galois group of the leaf is the whole group G. The second hypothesis is more subtle, and we will spend time on it at the beginning of the next lecture. So I will define it completely just after. Here, let's say that G is a good group. Is a good group. Okay, and I will define this term right after I finish to write all the hypotheses of the theorem. Then, if the Zariski closure of the curve gamma is small enough, so maybe small is something related to the dimension, so the dimension of the Zariski closure of your curve gamma is less, strictly less than the dimension of the group plus 1, so I have no explanation why I should write this and not less than or equal to dimension of G, but this is the way it is written in usual paper on Ax-Schanuel, so I keep this tradition here. So if you have that, then you will find an algebraic subvariety of X such that the projection of the Zariski closure is inside V. The Zariski closure of gamma is inside V. And it is even better like this, as this is this is an algebraic subvariety and this is just a projection. Usually the projection will be V up to some codimension 1, Zariski closed subset. Yeah. So this is the first part of our theorem. Let's say then A and B, the second part. The Galois group of the leaf intersected with V cross G. This Galois group is strictly included in G. So this is a leaf of omega restricted to V cross G equal to 0, which is the same kind of equation as the equation we have here, but you just restrict the form here in the matrix A to the subvariety V. Okay, so I will give there the definition and example of what is a good group, and then some comment about this statement just before the proof. So, the definition. So G is a good group if each time you take a sub-Lie algebra of E of G, sub-Lie algebra, then maybe H is not the Lie algebra of an algebraic group, but it is a sub-Lie algebra of a strict sub-algebraic group. So I'm writing this. There exists H, a subgroup of G, algebraic. So given by polynomial equations, such that H is included in the Lie algebra of H, which is itself different from the Lie algebra of G. So, meaning that the non-algebraic Lie algebra, so Lie algebra that are not Lie algebra of algebraic groups, the non-algebraic Lie algebra are not Zariski dense in the group. Okay, this is the definition of good group. Example. There is a nice, easy example. Do it. Is that the additive group here is good. In fact, the additive group is its own Lie algebra. So any sub-Lie algebra is a linear subspace. Any subgroup is a linear subspace too. Any Lie group is a linear subgroup. And then if H exists, it imposes the polynomial equation here, which are just linear, such that this equality holds here. The second example is what's called complex torus. Oh, yeah. It's not good. And in fact, so it's easy to get it's not good, but you can see it as a consequence of Ax theorem about the exponentials. So if you look at H in the Lie algebra of C star n, which is just Cn, defined by H equal the multiple of alpha 1 to alpha n, with alphas are Q linearly independent. Okay. Then the Lie group generated by this one is this set exponential of alpha 1 t exponential of alpha n t for t in C. So this is the Lie group that corresponds to this Lie algebra, but the Zariski closure of this one is everything. Okay. Otherwise, you will have relation between the exponential and by, let's say, Ax, but in fact, previous theorem from I don't know who, you will get a linear relation, Q linear dependency between these numbers here. Okay. Then the example we need are the following. So these are the toys examples. example just to be sure that there exist good and there exist no good groups. But then the third example is the SL2 of C. Okay, this is good. Why? Just take a Lie subalgebra of SL2. Then, in a good, up to a change of basis of C2 or up to a conjugation by an element of PSL2, you can assume H is included in a set of matrices like this. Yeah. So H is a set of triangular matrices, and this is a Lie algebra of an algebraic group. This is a Lie algebra of the same, of the group of invertible matrices of this shape. Okay. So H, let me just say this, is equal to 0 to be in small SL2. And then this is a Lie algebra of this one. And this is a strict subgroup of this one. So for this reason, PSL2 is good group. And the example, which is very important for us, will be this one. This product here is good. Okay, the proof of that will be the first part of the last lecture. Last part of the lecture. And in fact, it will be the key ingredient to prove Ax-Schanuel theorem from the theorem I just wrote here. And I am just erasing now. Okay, I have some remarks on this theorem. The first remark, if the dimension of X is equal to 1, then the dimension of leaves is equal to 1. And for this reason, as gamma is inside the leaf and is a non-constant curve, okay, when I say curve, I really mean curve and not point, so it's non-constant. The parametrization is not just a point. Then the two have the same dimension. Then the Zariski closure of gamma is the Zariski closure of the leaf. Yeah? But one of your hypotheses, yeah, the hypothesis 1, is that the dimension of this is the dimension of G plus the dimension of X. So plus 1. And another hypothesis is that assume that the dimension of this is strictly smaller than the dimension of G plus 1. So when X is a curve, the theorem, the hypotheses of the theorem are not compatible. You cannot apply your theorem. You cannot satisfy both hypotheses. So in this case, the theorem is empty. Okay? There's no situation where you can apply the theorem. Okay, and it is nice because we want to apply it for product of curves, so something that is much bigger than just one curve. Okay, then the second remark, that the hypothesis impose a condition that in general cannot happen. So your leaf L has codimension, which is the dimension of G. As remember that L is a graph, or locally is a graph of a function from x to g. So it has dimension, the dimension of L is the dimension of x, and the codimension is the dimension of g. And then your hypothesis is that the dimension of the Zariski closure of gamma is smaller or equal dimension of x, dimension of g. So in general, this kind of object can only intersect in point, yeah? Because you have not enough place. But your hypothesis is that the intersection is not transversal. Because in the intersection you have gamma. Yeah, gamma is in L, gamma is in its Zariski closure. And this has dimension 1. So the dimension of the intersection, or at least one irreducible component of the intersection, must be bigger than 1, which means that the intersection here is not transversal. So people call this unlikely intersection, or atypical intersection, or non-transversal intersection, if you want. So what is the strategy of the proof? So first I will, not to get many notation, I will write omega for the Zariski closure of gamma, which is so an algebraic subvariety of x times g. Remember that we have this form here, which is going from, so it's a one form defined on the whole space, taking value in the Lie algebra of G. And then the first step, we have to prove that there exists that the restriction of omega, so the step 1, is to prove that if you apply omega not to any tangent vector, but to tangent vector to z or to w, it will take value in a sub-Lie algebra, which is really a strict sub-Lie algebra, and then in the Lie algebra of a group. So this will in fact be included in the Lie algebra of H with H different from G, or let's say the Lie algebra of H, which will be different from the Lie algebra of G, with H as algebraic subgroup. So the two main ingredients here will be, or the three ingredients here will be, first, the equation satisfied by omega. Second, the fact that omega is not anything but the Zariski closure of a curve in the leaf. And the third is the fact that we are working with good groups. The step 2 Step 2 is to produce the variety V. In this way, you will look at the resultant of your Galois of the group H. Which is, okay, it is just a quotient map. By the right action of H on G. And then we will prove that the image of this W is included in the image of the leaf. The leaf on which we have taken our small curve. And now, this is algebraic. And this is not. It is not algebraic because the Galois group is not H. Remember that this subvariety of the quotient here is algebraic if and only if the Galois group of the leaf is included in H. Because Galois of L is not included in H. Choose as this has dimension equal to the dimension of X, then this has dimension strictly smaller than the dimension of X. And now, because this projection can be followed by the projection on X, you have that PR of W has dimension. The dimension of this is strictly smaller than the dimension of X. And we prove what we want, as this is a projection of an algebraic subvariety by an algebraic map. If it has a strictly smaller dimension, it means that it is included in a strict algebraic subvariety. Okay, and the last step, step 3, will consist of computing. Okay, it will be very the Galois group of this leaf that you restrict over you intersect, let's say, with V equals G, and it will be quite direct. Okay, let's go for step 1. Step 1, so I will give you a few lemmas, some easy, some more difficult, and then to derive the inclusion here. So first, I want to restrict my equation on this set. Yeah. So to restrict the equation on this set, and I want to be sure I still have equation, as I have some differential form with common kernel. If my subvariety V cut the kernel transversally, then my form will not have common kernel when restricted to W, and then I will not have this curve and differential equation, and I can only work with differential equation. So what I want to say here that for any P in W, the dimension of the kernel of omega restricted to T plus W. Okay, so there are 4 in in the whole tangent, so you can restrict to the subspace. You look at the intersection of all these forms, and this is strictly positive. Meaning that at any p I have a direction, a vector subspace of the tangent space that will give me the direction of the integral curve of this system. Okay, so the proof is done like this. So you just write, let's say, omega tilde is a set of points in omega such that the dimension is bigger or equal to 1. So the dimension of these is bigger or equal to 1. Now, the dimension of the kernel, these are linear systems with a parameter p. Yeah? So you can think of this as a matrix, not square matrix, rectangular matrix, with some parameter p inside. And you want to know, with a parameter, the dimension of the kernel is moving, and you want to be sure that it will not go down. And so to do so, you just remark that the dimension, okay, when the parameter is moving, the set of points where the kernel is growing will be given by annihilation of some minor of this matrix. Your matrix with a linear form of matrix, so with coefficient some rational function in P, and then the point where the rank is going down will be the point P that annihilate some minor of this matrix. So this is Zariski. This set is Zariski closed. Yeah. First is Zariski closed. Second, this set contains gamma. Yeah? Because if P is in gamma, if P is on the curve, then the tangent vector to the curve at P is in the kernel. Yeah, by definition, this curve is on a leaf. I mean, this curve, the tangent vector is always in the kernel of the big omega. So if it is in W and in the kernel of big omega, it is in the kernel of the restriction. So it is a Zariski closed set that contains this, but look at W, it is a Zariski closure of gamma. So W bar is W. Okay, and this is proved. Okay. Then, the second lemma. We need some computation, so I will write the lemma here. And the proof over there. So there exists H included in G, in the Lie algebra of G, which is a vector subspace, a subvector, a linear subspace, such that omega of TPW is equal to H. Yeah, for equal H, and I mean it's equal for P generic, and it's always a subspace of this. Generic P means P in W, but maybe not in a codimension 1 algebraic subvariety, closed algebraic subvariety of W. Okay, the proof is here. So you have all these forms here restricted to W. So from the coefficient maybe a better way, right? So you choose a basis. Choose a basis E1 to EK of your Lie algebra. Then you can write omega. It is just the sum of some one form times your element A of the Lie algebra. Yeah? Omega I are one form over X. And then you take the restriction to W. So this means that now these forms are on W. And you assume, so you can always assume that omega 1 to omega p are C of W independent. And omega p plus I can be written in terms of the previous one. In other words, okay, omega 1 to omega p is a basis that generates this form here. And so you have b, I, j, omega j, sum over j equal 1 to p. And this is for I equal 1 to, I have to go to k, so k minus b. And you can assume you have this relation. And then we are doing, and what, where do we use this lemma here? The red lemma. It implies that the rank of this matrix B is bigger or equal 1. Yeah? You have form, you have too many forms, they have common kernel, so there are some relation between them. Yeah? This is the common kernel, the dimension of W, which is smaller or equal k, plus the lemma. Right? So you have k form, they have something common in the kernel, so they must have a relation. Maybe I didn't want to say that, excuse me. So you have this, and what you have is P strictly smaller than K. Okay, if the form is 0, it's not a problem here. So you have, because d of W is smaller or equal K, and because of the lemma, so you have at most K form, but they have some relation here. at most k form on a vector space of dimension k with something common in the kernel, they must be related by something like this. Now, we want to prove that these b are in fact constant. Okay? The goal is to prove that b's are constant. So for this, you will choose a vector field on W. So I will call it D, so within a row, a vector field on W. You can think about a rational vector field on W if you want to be sure that it exists, and taking value in the kernel such that omega of D is 0. Okay. So all this kernel gives you a subvector bundle at the generic point of your vector space, your tangent space. So you can always find something like this just by solving linear system. So maybe to be sure, I will say a rational vector field on W. Now we have to do some differential calculus. Calculus using Lie derivatives and exterior product. Okay, so on one side you can take so I will call it the Lie derivative with respect to d of your omega. So for this you just do what you want to do, you take the flow of d, you pull back omega by the flow of d, you take the difference with d, and you let the time go into 0. You see first order, at the first order what kind of tensor you get. But you can also use what is called Carton Formula. So the contraction of your tensor with your vector field, but you take the derivative first. So this is two forms, so it is one kind of tensor here, and you do the contraction with a vector field, which is another kind of tensor. You do the d e of this vector field of omega. Yeah, this means that you take these two forms and you let these two forms eating this vector field at the first position of the two. But now this is 0. Okay, this is just omega of d. So this is 0. This is written here. And this, you can compute it because the omega is minus omega, which omega. Yeah, so if you do the contraction with d of big things, what you get is minus omega of d times d. This is for the first part. Remember that this is just, maybe there is a 1, no, there is no 1/2 here, minus, okay. This is exterior product, so it is antisymmetric. So you have here omega of d, which means that this is 0, as omega of d is 0 and omega of d is 0. Right? So the Lie algebra here, the derivative of this is 0, means that derivative of all the coefficients here with respect to d are 0. Then you apply this to this equation here. Apply to this relation. And what you get is that 0, which is the derivative of this one, is equal to the sum equals the sum j equal 1 to p of, you take the derivative of this one, LD of b I j times omega j plus b, you take the derivative of this one, but the derivative of this one is 0, plus 0. So what you get is a relation which has this shape here. You assume your first form are independent. So this implies that LD of B, I, J are all 0. But the Lie derivative, look this way. The contraction of the function is nothing, so this part does not exist. It is just the evaluation of the derivative. It is just the directional derivative of Bij. And as you choose any vector field in the kernel of omega, the fact that this is 0 means that Bij are constant on the whole leaf, on the intersection of the leaf L that we started with omega. Okay? Because the derivative in all the direction of the leaves are 0. And now look, here you have a rational function. Here you have something that contains gamma. Gamma is a risk-hidden in omega. So if a rational function is constant on the Zariski-Dance subset, then these are constant, and that's all. So you can erase it. Constant on omega. And so we prove that these are just constant on omega. And then you can write it this way. H, which is a set of combinations Ci, Ei, because these I are bases of the Lie algebra, such that C, the sum of these, Cp plus I is B, Ij, Cj, J equal 1 to P. This is a linear subspace, and the form satisfies the equation. So the form omega respect to W take values in this space here. So this gives the proof. Okay, then the step 2, no, I have to finish the Lie algebra. The lemma, next lemma, that H is a Lie subalgebra. Or a sub-Lie algebra. So for this, you just take E1 and E2 in H, and you want to say something about the Lie bracket. Yeah? But because they are in H, and because of the equality I just erased, that in almost any P, the image is exactly this one, this means that you can choose B1 and B2 rational vector fields. On W, such that omega of V1 is E1, and omega of V2 is E2. And then you use your nice equation that we already used here. And you compute d omega evaluated in B1, B2. And this is d will be omega of V1, omega of V2, or maybe there's a minus here, plus omega of V2, omega of V1, which is exactly the Lie bracket. Okay, this is which is the Lie bracket of omega minus the Lie bracket of omega of V1, omega of V2, which is the vector we want to understand. And now look, omega is a one form with value in a certain Lie algebra. When you take d of omega, you will get a two form with value in the same Lie algebra. The Lie algebra, the fact that the value of omega are in H is given by this constant coefficient linear relation. And then if you take the Lie derivative here of this, or the differential of this, the exterior differential of this one, because they are constant, you have just a d here. So if omega takes a value in the Lie algebra, its differential will take value in the same Lie algebra. And this value on this vector here are exactly the bracket we want. So this proves the lemma. So we achieved step 1. Okay, let's go for step 2. It is easier, and step 3. Okay, so step 2. So on step 2 I already gave all the argument, no? So we have a leaf which is in x cross g, which is integral leaf of our differential equation. We have the map Q, which is a quotient map from x cross g to x cross g over h. Yeah, and we have some map L, we go from the Lie algebra of G to the Lie algebra of G over maybe I have to once just before step 2 here. As H is a sub-Lie algebra but different of Lie of G, and G is good, then we can assume H no, we have that H is in the Lie algebra of an algebraic group here. Yeah? And then H is a sub-Lie group, H is a sub-algebraic group of G that satisfies that. Okay? The hypothesis good is here just to ensure that we get such a group. Okay, so we have these three things here, and now we will look at the path system. L omega is equal to 0. So omega takes value in the Lie of G, and you compose with that. So you take some of the form annihilated by omega. So, and you take G, a leaf of this system. So I can draw what is happening. You have your group G, you have your base, which is X here. You have your leaf, which is analytic here, and then this space here is just, so this L has dimension, the dimension of X, and it's the graph of a function, locally the graph of a function, and then you, to each point here, you take the H orbit. Yeah? So this is a point in this space, and then you take the orbit by H acting this way. So all this here will be G. So it is a leaf of this system with L inside. Yeah. And we will see that we also have W inside. So as omega of the tangent of L 0, no, it's not this one, that will help us. So L is included in G. This means that gamma is included in G, in this leaf here. Gamma is in L, so there's no problem. But then, if you compute L omega of TW, this is 0. We did this in order to get 0. And then this, this space omega is included in the leaf. Yeah. And the intersection with this leaf is non-zero, and leaves are disjoint. So this implies that omega is inside this G. So omega is something here. So your curve is a small thing here, and omega is something, I don't know, it is a risky close, but it is something that is not in the white leaf, it is in the green one, and intersect the leaf at least in the curve gamma, which is here. Okay, and what else? So as I said, all the orbits, if I will say it this way, if you take an orbit x cross GH, so you fix x, take an element here, and you take the orbit by h, and you look at the tangent of this. This is also in the annihilated by L. Oh, I put a small letter here, but it was a big letter, right? And this is 0. This is the main property of the form omega I told you in the lecture, the end of lecture 2, yeah, that omega will send the infinitesimal generator on the right, so that generates the tangent of the orbits, onto its Lie algebra. Yeah. But then L killed this Lie algebra, so it is 0. So with all of this, you can see that rho, so now you take rho, which is something that is going to the, so x does not move, and you have the quotient here. And what you see is that because rho killed the action of H, and G is built from L by taking orbits, you have here that the green and the white are the same. Now, rho of G is equal to rho of L. And L is really transversal to the action of G, so the dimension of L of this is the dimension of X. Right? And our hypothesis on L is that the Galois group is not H. It is bigger than H. It is not included in H. So this is not algebraic. But omega, W is included in G. So here you have rho of W. And W is algebraic, rho is an algebraic map, so this is algebraic. Now the dimension of this is equal to the dimension of X, then you have a problem here. Yeah? Because in particular, it will mean that you will find enough polynomial vanishing of this one, and they will vanish on some connected component of this, which is connected. So it will vanish on this, and this will be algebraic. So this will imply this and the inclusion into something that is not algebraic will imply that the dimension of rho of W is strictly less than n. And now, as I said, if you get here something of dimension less than n, then when you do the projection on X, you have something that may be even smaller. But in fact, no, it is not smaller, it has the same dimension. I will write this way. Okay, this is step 2, and so this is what we call W in the statement of the theorem. And now to finish for today, we get step 3. And this is easier. So so you see here W now is somewhere here. Yeah? It is algebraic, but it is in a leaf. It is in a graph of a function from x to this quotient. These are graphs of function. So, graph of function here are are local biholomorphism. So the dimension of this and the dimension of this are the same. So you have the dimension of X is equal to the dimension of V, not X, W. Yeah? So your W here is somewhere there. Okay, now, sorry for that, dimension of rho of W. Yeah? The rho is here in the quotient space. But you have also that rho of W is included in rho of the leaf intersecting with this. Yeah? You see? Your curve here is a curve here. As it projected here, yeah, then it is all above and it projects inside here. Yes? And this has dimension equal to the dimension of V. Yeah, again, for the same reason, it is a graph here. And it contains something algebraic which has the same dimension. So rho of this, when I say this as dimension. So if you take here the rho of this one, it's something you don't really know, it's a graph of a holomorphic function, but it contains, with the same dimension, an algebraic subvariety, so it must be algebraic. If you go back to the definition of the main property of the resultant equation, this will imply that the Galois group of this is included in H. If it is included in H, it's strictly smaller than the G we are looking at. So what does it mean? It means that this leaf may be transcendental, but restricted to this algebraic subvariety, it became less transcendental. It has some polynomial equation, okay? And the main example is just the example we get from Ax theorem. So if you take 1, 1, y2, 2 function, and you look the map to a map to, let's say, the logarithm of y1, the logarithm of y2. Yeah, so this map, the graph of this map is Zariski length in C star square times C square. Yeah. But if you take restriction to line, let's say, if you take restriction to line, this line, for instance, then you will see that the two functions you get are no more independent. Yeah? So this is V, this is the equation of V, and now you restrict to V plus C2. Your graph here is the risky length here, but when you take restriction to this one, it is no more the risky length. So L bar is everything, but if you take the intersection, the restriction to V, and you take bar, it is strictly included in this one. So there are variety that gives you a special kind of relation that does not appear at this level. Okay, so next lecture we will see how to prove a part of Ax-Schanuel theorem for the function j using the theorem we just proved today.